Now this is one of my favorites. I've used this deep sky object a couple of times before because it's one of my favorites and I can. And this particular system, Chandra imaged 2 white dwarfs. Okay? Now remember, there's a huge amount of low mass stars. The mass distribution of stars is sort of similar to the food chain. You have a few top predators, you have a few top massive stars. And the further you go down, the more and more stars you have. So there's billions and billions and billions of low mass stars. Okay, so, and solar mass sized stars. And all of those are going to eventually become a white dwarf. Out of those billions and billions and billions of stars, about 2/3 of them are in binary or multiple star systems, because when that proto star collapses finally into the disk and fusion starts, it still has to obey those elegant laws of physics. It has to conserve angular momentum. And there's only 2 ways to do that. You can either form a multiple star system or a single star with a planetary system. Okay? So there's tons of these scenarios out there, but Chandra managed to catch these 2 white dwarfs that are only 50,000 miles apart. They're orbiting each other at 1,000,000 miles an hour every 5 minutes. They are, because you can tell by the light curve that it is slowing down by 1.2 milliseconds a year, which means they're moving closer together by 2 feet every single day. Eventually, they are going to come together. Okay? And when they come together, actually this isn't going to be too spectacular because these are low mass white dwarfs. They're each about 1/2 solar mass. So when they come together, they will be about 1 solar mass. And you can still stay a white dwarf at 1 solar mass. Because of Chandrasekhar's limit. Now, Chandrasekhar's limit says that for a white dwarf to hold itself together and not collapse any further, then it cannot exceed 1.4 solar masses. Now, we said that a living star is being held in equilibrium by radiation pressure out, gravity in. A white dwarf is held in equilibrium by degenerate matter, neutron degeneracy pressure. You can sort of, it isn't really this, but you can think of it as atom against atom, electron cloud against electron cloud, electron repulsion. What it really means is Pauli's exclusion principle is at work here. Every single space can only be occupied by 2 electrons with an opposite spin. Every single space within that white dwarf is occupied by an electron. There's no room for anything else, not one single little electron. Okay, so at 1.4 solar masses, then the electron repulsion isn't strong enough to stop gravity from contracting the white dwarf anymore. Okay, so here, with this particular one, because when they come together, they will only have 1 solar mass, they can still stay a white dwarf. But what if you have 2 white dwarfs that when they finally come together, they will exceed Chandrasekhar's limit? Well, if they only end up at about 2.4 solar masses or so, they could be a neutron star. That's another way a neutron star forms, from 2 white dwarfs. Or, if there's really too much, when they start to come closer and closer together, then as soon as Chandrasekhar's limit starts to be exceeded, and there's too much mass that a neutron star can form, then you have a problem. It gets so hot that it starts fusion of the carbon in the core, and you have a runaway thermonuclear event within the white dwarf that totally destroys the white dwarf and leads to the type 1a supernova event. So a type 1a supernova is the thermonuclear destruction of a white dwarf.